Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 33, Organic Chemistry 1. Today we will continue on chapter 8, Structure, Synthesis and Reactions of Alkenes. Today we will continue on reactions of alkenes, addition of water, what we call it hydration reaction. In the previous lecture, we have covered two methods to add water to alkenes. The first one, acid catalyzed hydration using water and sulfuric acid. And second method, mercuration-demercuration method. And both led to the formation of what we call Markovnikov product, where the hydrogen is attached to the carbon carrying more hydrogen and the OH on the other carbon. Today we will talk about Hydroboration-Oxidation method, and in this case we take the alkene in two steps, add borane and tetrahydrofurane, and then the product is treated with hydrogen peroxide in base to give alcohol in anti-Markovnikov orientation, where the hydrogen is attached to the carbon carrying less hydrogen. And also the addition is syn addition. So if we start with methyl cyclohexene, treated with borane and tetrahydrofurane, and then hydrogen peroxide in presence of hydroxide, we get alcohol anti-Markovnikov orientation. And hydrogen and OH are in the same direction. So it is both, in this case, above the plane. And it's enantiomer, where the hydrogen and the OH below the plane. We don't get the hydrogen up and OH down, the trans addition. These isomers are not formed. Only syn addition products are isolated. Again, in racemic mixture, which means that you always get enantiomers. Recall from lecture 4 on Lewis structure, the diborane do exist as a dimer from borane, where we have 3 atoms, 2 electrons, or 2 electrons, 3 center bond called banana bond between the boron hydrogen and boron atom. And the borane is Lewis acid, electron deficient, in presence of ether as a protic solvent, and tetrahydrofurane here is an example of cyclic ether, will form with a borane Lewis acid Lewis base complex to stabilize the mechanism. Hydroboration, the preference for pH2 to be positioned at the less substituted carbon, can be explained in terms of electronic considerations or steric consideration. In the first step, attack of the pi bond triggers a simultaneous hydride shift. However, this process does not have to be perfectly simultaneous. As the pi bond attacks the MTP orbital of the boron, one of the vinylic position can begin to develop a partial positive charge. This developing partially positive then trigger a hydride shift. to form alkyl borane. This step is repeated for each pH to form trialkyl borane. In the second step, oxidation step, the hydroxide ion acts as a base and abstract hydrogen from hydrogen peroxide to form hydroperoxide ion. The hydroperoxide ion acts as a nucleophile and attacks the boron center of the trialkyl borane, followed by alkyl shift to form alkoxy borane. We need to repeat these first three steps twice to form the trialkoxy borane, which then attacked by the hydroxide ion as a nucleophile, followed by expel of alkoxide ion, which is protonated by hydrogen from water molecule to form alcohol. Steric consideration. In the first step of the proposed mechanism, both hydrogen and BH2 are adding across a double bond simultaneously. Since BH2 is bigger than H, the transition state will be less crowded and lower in energy if the BH2 group is positioned at the less sterically hindered position. Here, the BH2 is positioned at the less hindered position. The transition state is anti-Markovnikov orientation. If we look in here, the BH2 in the crowded area, so the transition state will be higher in energy, less stable, and this addition is Markovnikov orientation. Show how you would convert 1-methyl cyclopentanol to 2-methyl cyclopentanol. 1-methyl cyclopentanol to 2-methyl cyclopentanol. If we look here, we have alcohol. Carbon as an H, adjacent to carbon has an OH. So this could come from alkene, hydration of alkene. And again, the alkene can get you can get it from alcohol by dehydration. So if we start by 1-methyl cyclopentanol heated up in sulfuric acid, we get the alkene. Now, this carbon has H, and this carbon no hydrogen. Well, I need now the OH to link to that carbon. Okay? So it is anti-Markovnikov. How do we add water? Anti-Markovnikov. We use hydroboration-oxidation method. So we treat the alkene with borane and tetrahydrofurane, followed by hydrogen peroxide in base. We get the anti-Markovnikov product, 2-methyl cyclopentanol. A norbornene molecule labeled with deuterium is subjected to hydroboration-oxidation, give the structure of the intermediates and the product. Here is the compound bicyclo 2,2,1-hept-2-ene-2,3 deuterium, deuterated. That is the compound norbornene. When we treat it with BH3, we know that the addition is what we call it syn addition. addition of HbH2, okay, from the same side. So since the exo phase, that's what we expect, the addition from this less crowded, so the addition of B and H2 and H will come from that side. Okay, so the hydrogen up, and we'll see that the BH2 here is up too. We get that, and we get the mirror image of it. Okay, you can take this molecule and rotate it 180 degrees. You see the double bond in this area, okay, here, and then add H and BH2 from the exo phase, not the endo phase, okay, from the exo phase, and they are mirror image. We treat that with these compounds with hydrogen peroxide in base. We get, instead of BH2, we get OH, alcohol. So we get 1s2s3r4r bicyclo 2,2,1 heptane 2,3 G2,2ol, and the enantiomer. Predict the major products of the reaction of trans 4,4-dimethyl pent-2-ene and borane and tetrahydrofuran, followed by hydrogen peroxide in base. Include steric chemistry where applicable. In the this example and the coming one, you have to build up your skills on drawing in 3 dimensions. So I used 2 different ways of presenting the reaction. Here we start with the trans 4,4-dimethyl pent-2-ene. The plane of this molecule, I draw it perpendicular to the screen of your computer or laptop. Now, the borane will add in what we call it syn addition. So either the H and boron will come from the top, okay, or from the bottom, and they will be in the plane of the screen. They will be in the plane of the screen, right? Then the second step, we replace the boron or dialkyl borane function with OH. So OH will be down or up. We started again with the trans in the plane perpendicular to the screen. So the tertiary butyl group will be in the back, and the methyl group will be in front. Then the borane will add from top or bottom, from here or there, okay, to form these 2 enantiomer at the end, R or S. We can imagine also that the other way around, that the boron will add to this carbon and the hydrogen to that carbon. But as we mentioned before, that there is 2 factors affecting the regioselectivity and stereoselectivity of the final product: electronic and steric. Okay, now the BH2 is much more bulkier than hydrogen, and in here we have a tertiary butyl, so this transition state will be unstable due to the steric effect. Why you are saying that the boron should be added this way too? Remember that we have here hydrogen and we have here another hydrogen. So we cannot say Markovnikov or anti-Markovnikov. These are the same number of hydrogen. Okay? So this one will be less stable. Again, here is the bulky. Remember, they are perpendicular to each other. Okay? So this is also the same stability as this one. Okay, so we'll add BH2 in here, BH2 in here, then OH in here after the treatment with hydrogen peroxide base. Okay, and then again we get S and we get R. Okay, so these products will be minor, while the previous one will be major. When Z3-methyl hex 3-ene undergoes hydroboration-oxidation, two isomeric products are formed. Give their structures and label each asymmetric carbon atom R or S. What is the relation between these isomers? Repeat the part A. To E methyl hex 3-ene, what is the relation between the products formed from Z and those from E? In this example, I put the molecule to be in the plane of the screen. Okay? The molecule in the plane of screen. So the pi bond will be perpendicular to that plane, and the boron will add either from front or from the back. In front, so after the treatment with boron followed by hydrogen peroxide, the OH will be in front, and hydrogen, since it is syn addition, or the hydrogen and OH will be in the back. Now, when I draw it this way, I decided to hold the molecule from these two. I hold it, so it will not be moving. Okay? And then when I put the hydrogen and OH from front, this methyl and this hydrogen will go in the back. So this hydrogen and this methyl will be in the back. Okay. Now I still holding the molecule from here. Okay. Now you add the H and OH from the back. Then this hydrogen will be in front and this methyl will be in front. In front, in front. Now come to the E isomer. Hold the molecule from here, these two. Hold them. Okay. Now, if we add the OH in here and the H in here from front, this one will be in the back and the hydrogen on that carbon will be in the back. And H and OH will be in front. Okay, that's it. If the H and OH come from the back, then the hydrogen will be in front and the ethyl group will be in front. Now we have in the upper one we have 3s, 4s, and the other enantiomer will be 3r and 4s. In the E isomer we get 3s, 4r, 3r, 4s. The relation here between these two, these are enantiomers, and here again these two are enantiomers, and the relation between any one of up and down, they are distereomers. They are not mirror image to one another, while in each case two products mirror image to one another, and the product is a racemic mixture, optically inactive. Addition of halogens, halogenation reaction. Halogenation of alkenes is only practical for the addition of chlorine or bromine. The reaction with fluorine is too violent, and the reaction with iodine often produces very low yields. For most simple alkanes, halogenation appears to proceed primarily via an anti-addition. For example, consider the products that are formed when cyclobentene is treated with molecular bromine, Br2. Cyclobentene with bromine in carbon tetrachloride affords 1R, 2R, 1,2-dibromocyclobentane, and 1s2s, 1,2-dibromocyclobentane, and these are racemic mixture. These are enantiomers. Okay, notice that the addition Br, one is up and one is down, one is down, one is up, so it is anti-addition reaction. We have to find out. Halogen addition is another example of stereospecific reaction. We start with Z, we get enantiomers of 2R, 3R, 2S, 3S, 2,3-dibromobutane. When we start with the trans or E isomer, we get again a compound, but in this case it's meso, so it is 2R, 3S, and the meso compound, one compound, it doesn't have enantiomer. So meso compound, it has a plane of symmetry. If just we move this, rotate it, will form this, and again this is a mirror image. So it is R and S. Mechanism for this reaction: if we start with Z3-methyl bent-2-ene, the electron clouds of the pi bond will attack on the partially positive Br, kicking Br minus out, leading to the formation of bridged bromonium ion, which is in resonance with these two structures. The Br bromide anion will attack on the partially positive carbon carrying more substituent, okay, because that will be a tertiary carbocation, so the contribution in resonance will be higher. Br will attack on that, okay, leading to the formation of Br2 Br bond in opposite direction, what we call it anti-addition, okay, plus enantiomer. Okay, how this enantiomer formed? As we know, the double bond has two enantiotopic phases, upper phase and bottom phase. Okay, now if the bottom phase attacks on the partially positive, will form this bromonium ion, which is enantiomer mirror image to the first bromonium ion showed in the previous slide. Again, this bromonium ion is in resonance with these two structures. Br minus will attack on the partially positive carrying more substituent to form again the enantiomer, which is 2R, 3R, 2,3-dibromo 3-methyl pentane. Halohydrin formation. When bromination occurs in a non-nucleophilic solvent such as chloroform, the result in the addition of Br2 across the pi bond. However, when the reaction is performed in the presence of water, the bromonium ion that is initially formed can be captured by water molecule rather than bromine. Predict the major products for the following reaction. Bromine in water added to Z3-methyl bent-2-ene. We need to know what are the products. In the first step, the bromine is added, and with the formation of bromonium ion intermediate, which in resonance with delta positive on that carbon and delta positive on that carbon, and which one is much more predominant? Of course, the more substituted carbocation or the partially positive carbocation is more stable, so the water will attack on this carbon, forming the oxonium ion, followed by deprotonation or with proton transfer to form the alcohol, or we call it here, it's bromohydrin. It's bromohydrin. Okay, that's 2S, 3S, 2-bromo 3-methyl pentane 3-ol, of course, plus enantiomer. What do you mean? I mean that you can have the upper face of the pi bond attack on the bromine, will give this compound. The other enantiomer will come from the bottom face, will attack the Br. Okay, and the same step, but we get 2R, 3R, 2-bromo 3-methyl pentane 3-ol as the enantiomer. In 50-50, the probability of the upper face to attack the bromine or the bottom face to attack the bromine is 50-50, because we have a plane. It's the two faces are what we call it enantiotopic faces. Okay, remember that I draw it perpendicular to your screen. Okay, here is the bottom to get the other enantiomer. Then the OH will attack on this carbon, the more substituted, of course, followed by deprotonation to give 2R, 3R, bromo 3-methyl pentane 3-ol. Show how you would accomplish the following synthetic conversions: 3-methyl bent-2-ene to true chloro 3-methyl pentane 3-ol. This is the structure of 3-methyl bent-2-ene. So we have here carbon double bond, where this one carries one hydrogen, and this carbon carrying no hydrogen. We would like the chlor to be added to here, Cl, and we add here OH. To do that is straightforward. One step, adding Cl2 in water, we get 2-chloro-3-methylpentane 3-ol, or what we call it 3-methylpentane chlorohydrin. In B, chlorocyclohexane to trans 2-chlorocyclohexanol. Okay, we start with chlorocyclohexane with potassium hydroxide, so we eliminate HCl and form cyclohexene, and then again add chlorine water, we get trans 2-chlorocyclobentanol, or what we call another name, cyclohexene chlorohydrin. In the last one is 1-methylcyclobentanol to 2-chloro-1-methylcyclobentanol. So we take 1-methylcyclobentanol, add sulfuric acid and heat, we form methylcyclobentene. We add chlorine and water. The Cl will add to the carbon carrying more hydrogen. So here we are, and then we add the OH to the more substituted carbon, and we get 1, 2. So it is 2-chloro-1-methylcyclobentanol. See you in the coming lecture. Bye bye.